welcome to another exciting set of notes. This time we're going to be talking about infinite series. This is the fifth set of notes in our sequence and series sections, chapter, whatever you want to call it. Okay, so first thing we got to talk about is what is an infinite series. So an infinite series is a series that never ends. A series, use the pen, a series that never ends. Okay, so the important thing to know about these is sometimes there's a sum, sometimes there's not a sum. It's kind of hard to tell. So we're going to go through and look at 6 different series and see if there's a sum or not a sum. So our first series is one that may look familiar. It's 1 plus 2 plus 3 plus 4 plus 5. And this tells us that it is the following sum in summation notation. So it goes from n equals 1 to infinity, and it's just n right there. And then in order to show you guys what this would look like, I graphed them all. Okay, and I graphed them using Desmos so we could see the sum. So right here, we can see that the orange line is our the values each term, and the black dots, this is our sum. So when n is 6, my sum is 21. Okay, and you guys can see that no matter how big we make n, these values over here, this 641 or 6,441 down here, will always keep going up. And even if I make this a really, really big number, so if I change this to 1,000, this number here is still going to keep getting bigger and bigger and bigger. This means there's no sum, okay, contrary to anything you might have seen. So this has no sum, all right? Let's look at this one. All right, so this is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Okay, well this is just the sum from n equals 1 to infinity of 1 over n. Let's look at this one. Go back to Desmos. All right, right here. Okay, well this one, it kind of looks like it's going to be approaching something because it's kind of tapering off like this. So it looks like it's narrowing down and getting closer to something. But if you look, I'm at 1,000 and it's still going up by like 0.1 each time. If I put 2,000 in here, it'll still have gone up. So this one actually doesn't have a sum either. It just keeps getting bigger and bigger and bigger. Really slowly it gets bigger, but it does keep getting bigger. This is actually a pretty interesting series. So this also has no sum. It's called a harmonic series. It's an important one. We'll talk about it at some point. All right, this one here, this one looks a little bit different. And really what we're doing here is we're looking at partial sums. We're using partial sums to figure out what's going on and going through and so forth and blah, 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 blah. But this one here, we can kind of see what's going to happen. It's going to be 0.3 and then 0.33 when I add in this, and then 3.3 and then 3.3 and then 3.3. So I might think this should sum to 1/3. Well, let's write it in summation notation. This one's a little bit weird. Equals 1 to infinity. And I know this is going to be 3 divided by 10 to the n. If we go to Desmos, we can see that it does in fact sum to 1/3. The bigger value we plug in for our n, the closer and more it gets to 1/3. Okay. Next one. This one looks pretty familiar. This is actually geometric, which is something we know and love. This is just the sum from n equals 1 to infinity, and then it's just 1/2 to the n right here. So 1/2 to the n, and let's see if this one has a sum. Over to Desmos we go. All right, this one has a sum of 1, and you can see that the closer, each time you take a partial sum, it gets closer and closer and closer and closer to 1. So when we take the 7th partial sum, it's 0.9921. When we take the 14th partial sum, it's 0.99938. So it's getting closer and closer to 1. Okay, so that's that type right there. Well, it's just 1. Okay, this has a sum of 1. All right, now we get exciting stuff happening here because these alternate negative to positive. This first one is just the sum from n equals 1 to infinity of negative 2 to the, not 2, n minus 1. Okay, the sum from 1 to infinity of negative 2 to the n minus 1. That spits out this series here. Let's look at Desmos. All right, this is really cool. Because we're flipping from negative to positive to negative to positive to negative to positive, this thing here looks really, really cool. You can see that it keeps doing that. It keeps bouncing back and forth, back and forth, back and forth. And eventually it's going to start bouncing back and forth, back and forth, back and forth a lot, like a huge amount each time. And you won't even be able to see what is going on. You won't see this cool like bounce back and forth thing. But this is a kind of a cool looking series here. I mean, it's cool. But it definitely doesn't have a sum because you're going to keep bouncing back and forth. You're going to get a really, really big negative number and then a really, really big positive number for really high values of n. So this one has no sum. All right, last but not least, 12, negative 9, 27 over 4. Well, this is just 12, and then this negative 9 is really, well, I'm willing to bet it's going to be, let's go 18 over 2 maybe? I don't know. Something like that. But I know the sum is going to be 12 times negative 3/4 to the n minus 1. So this n equals 1 to infinity. Now let's go check out this one. This one's even cooler than the last one. All right, this one bounces back and forth again because it has that negative thing, but it doesn't bounce back and forth and get really, really big. It starts to get really, really, well, not small even, but it starts to narrow down. It gets closer and closer and closer to a single value. Okay, you can see this black line here. I'm going to turn off this one because it's a little bit confusing. These partial sums here start to get closer and closer and closer to a single value. And this value is actually 48/7 clearly. You can see it bounces back and forth around this line. It kind of oscillates through it, which is pretty cool. All right, so this has a sum of 48 over 7. All right. Now, there's some terminology that we need to know. It's very important, and it's called convergence or divergence, and you have to be really, really careful with these definitions because we, me included, are not amazing, spectacular mathematicians who know all sorts of magical math that can make weird things happen. We aren't those kind of mathematicians. So, for our purposes, if a series converges, it means it has a sum. If a series diverges, it means there is no sum. So when there's an infinite series and converges, it has a sum. When it's an infinite series and diverges, it has no sum. So in some cases, you can evaluate an infinite series. I just said that. So as n increases, its partial sum gets closer and closer to a single number s. When an infinite series cannot be evaluated, you say it diverges, meaning that as n increases, its sequence of partial sums does not get closer and closer to a single number. So, geometric series, we have an infinite geometric series. You can easily tell if it's going to converge or diverge by looking at the value of r. So if the absolute value of r is less than 1, the infinite geometric series converges. If the absolute value of r is greater than 1, the infinite geometric series diverges. This is really important. For our purposes, arithmetic series never converge. Ever converge. Full stop. They never converge. Geometric series can converge. And here's a couple examples. Figure out your r value. For this first one, r is 1/3. That's less than 1, so it converges. All right, next one. R is negative 2/3. And the absolute value of this is less than 1, so it also converges. All right, this one right here, it's 5, 10, 20, 40, so this is times 2, so this is r equals 2. This diverges because it's greater than 1. All right, so you now know that an infinite geometric series converges when the absolute value of its common ratio is less than 1. Can you determine to what number the infinite geometric series converges? It turns out you can with this formula. Good job, Mr. Babcock. Thanks for leading your students to that wonderful fact. So an infinite geometric series with r, absolute value of r less than 1, converges to the sum s equals the first term, a sub 1, divided by 1 minus r, the common ratio. And this is yet another formula that you have to memorize. Okay, let's go and use it real quick, and then we'll be done. And you guys can go do the IXLs or something like that, I don't know. All right, evaluate each infinite geometric series. Okay, first step is always to find r. This one looks real familiar. r is 1/3. The second step is to write down the first term. A sub 1 is 2. Then put it into the formula. First term divided by 1 minus r. And that's clearly 3. You may ask me, Mr. Babcock, how did you get 3? Well, I used my calculator, kids. I used my calculator. You didn't see me do it, just like I won't see you use yours. Next one. A sub 1 is equal to 1. R is equal to negative 2/3. These are just the things we just did. Like, this isn't even fun. All right, plug it into the formula. You got to be a little bit careful here because it's 1 minus negative 2/3, and this is clearly 0.6. Again, I used a calculator. It's not very exciting. All right, this next one here, r is equal to 1/3. A sub 1 is equal to 2, so I got 2 divided by 1 minus 1/3. That we know is 3. You may ask me how I got 3, and the reason is because it's the same as this problem up here. They're the same, so I didn't have to use my calculator for that one. All right, this one right here, a sub 1 is clearly equal to, plug in 1 up here, I got 0.4 to the first, that's going to be 0.4. Okay, r is the thing being raised to the exponent, that's clearly also 0.4. Okay, that's great. I'm very excited to see that, so I got 0.4 divided by 1 minus 0.4, which is clearly 2/3. And you may be asking yourself, how did I do that? And I did not use a calculator for that because it's 0.4 over 0.6, which is clearly equal to 2/3 because I'm a mathematician. All right, and this one diverges. I can just tell you that right away because it starts with 2. R is 2. R equals 2, so it diverges. Done, no questions asked. All right, those are the notes. Good luck on the IXL and these questions that I have after. And then I have a video that's in response to the other video that I gave you guys last week where it was like, yeah, clearly 1 plus 2 plus 3 plus 4 plus 5, if you do it infinitely, is negative 1/12, which is total malarkey for the math that we know. And you can't just go using weird math that you find on the street. You have to know where it comes from. It's bad if you don't know where your math comes from, you guys, to make sure it's good math that you understand before you start using it. All right, have a nice day, you guys.